All right, class, today we're going to compare speed of sound in air and in water. This is a four-part problem, so we're going to do one part at a time, work our way through it, and see what happens as we go along. First of all, a couple things you need to know. Speed of sound in matter depends on density of the matter, as well as how easy it is to compress, called the bulk modulus. It's measured in pascals, which is the standard SI unit of pressure. 1 Pascal is 1 Newton per meter. The bulk modulus is defined as the increase in pressure or change in pressure divided by the fractional volume change caused by this pressure increase. So part 1 says a pressure increase of 100 kilopascals compresses a volume of water by 0.005%. So first it wants to define the bulk modulus. So to do that, we know that the bulk modulus, I guess I should say this is part 1, is defined as, again, change in pressure or increase in pressure divided by fractional volume, I'll just call VF. Well, we know that the change in pressure is 100 kilopascals, which is 100 times 10 to the third. We want to put it in just pascals, divided by a percentage, which is 0.00005. If you notice, I had to move the decimal place over two more places because it was a percentage, which gives us a bulk modulus of 2,000, or so 2.00 times 10 to the 9th pascals, which, if you want to put it in shorter terms, that's just 2,000 megapascals. Either way is the same, right? So that's part 1, just figuring out what the bulk modulus is. Part 2 now says we know that the speed of sound in a medium is given by velocity, or speed is divided by the square root of the bulk modulus divided by the density. So in this case, we want to know the velocity in seawater. Okay. All right, so if we do this, let me get to a new page. We're going to go to part 2, trying to find it in seawater. So again, just our equation is square root of V over rho. Okay, so seawater, which I don't give you, you had to look up, is a density, so the rho of seawater, of 1,000 kilograms per meter cubed. A little heavier than regular water because of the salt content. So to figure this out, we just take that, and it gave us the bulk modulus of seawater to be 2,100 megapascals. So that's 2.1 times 10 to the 9th pascals over 1.0 times 10 to the third kilograms per meter cubed. We're going to take the square root of that whole thing. Gives us a velocity, if you plug that into a calculator, of 1,450 meters per second. So that's the velocity in seawater. Okay. Part 3, which is our next part, says that a ship emits a sound burst frequency of 40 kilohertz to detect a submarine in water. Using our answer to part 2, which again was 1,450 meters per second, we want to know what the wavelength of sound for this wave is. So to do this, we need to know that velocity equals frequency times wavelength. So we know that velocity equals or wavelength times frequency, either way you want to put it. So if we were trying to solve for wavelength, do a little bit of algebra, we get wavelength is just velocity divided by frequency. Or velocity, we just said, was 1,450 meters per second. We divide that by our frequency that it gave us of 40 kilohertz, which is 40 times 10 to the third hertz. You always want to go back to hertz, don't want kilo in there, which is going to give us a wavelength of 0.036 meters, but doesn't mean a whole lot, so let's just say 3.6 centimeters. So it gives us a wavelength. doing pretty good so far. We now know that our last part, part 4, ship sonar operator hears the reflected sound reach him 5 seconds later. So he knows it takes him 5 seconds to do what? Get to the other submarine and back. So 2.5 seconds each direction, assuming that there is no change in velocity. Okay? So all we have to do here is, well, we have our guy, and then there's a sub. Takes 5 seconds to get there and back. So that means 2.5 seconds each direction, as we just said. So velocity equals distance over time. By the way, we are trying to figure out how far the submarine is. I don't remember if I just mentioned that. So if we're trying to find displacement or distance, that's just distance equals velocity times time. Well, we just figured out the velocity a little bit ago, and we know how long it took each direction. So we could just simply plug in our velocity of 1450 meters per second that we got from part 1. No, sorry, part 2. And then our time of 2.5 seconds gives us a total distance away of 3,625 meters, which is about 3.6 kilometers away.